Thanks. So yes, I'm Vincent Menoret. I'm from Exail Quantum Systems, which is a company in France. And today I will introduce what we do in the field of quantum sensors, specifically applied to geophysics. So as I said, we are a company in France. We were originally created as a small company more than 10 years ago called Mucans, and we were acquired by Exail a couple of years ago. So Exail is quite a big group. It's over 2,000 people. And in the quantum systems division, we are something like 45 people. We're specialized in quantum systems for high precision measurement and metrology. We now have systems that are in operation all around the world, several kinds of products. And today I'll specifically talk about gravity sensors that we build. Something that's maybe worth mentioning is that Exail is very vertically integrated as a company. So in my division, we build these quantum sensing instruments for geophysics, but more or less everything in there can be manufactured by Exail. In particular, all the optics and photonics that go in there. So we make our own doped fibers, we make our own laser sources, which we can in turn integrate into modules and then into bigger subsystems and into the final system. And with this vertical integration, we understand and control everything that goes into our products, which makes the whole approach very coherent, and we can make sure that we understand everything in our systems. And this is quite important because building a quantum system that can go on the field is quite a challenge. I kind of like this picture. The picture on the left is what a quantum gravity sensor would look like when we started. And this is what our systems look like now. So as you can see, we've done a bit of work on the engineering side of things. And so this is what the gravity sensor that we manufacture looks like. It's made of two parts. The cylinder on the right here hosts a vacuum chamber where we trap atoms in a vacuum chamber using lasers. And we have basically this cloud of atoms that we can drop, and we measure its acceleration as it falls. And that's the value of gravity we can get. So it's all completely integrated. So as I said, we design everything in there in-house, the electronics, the software, the vacuum. We've put a lot of efforts into making the device very robust, very easy to set up. It's only a few cables that you have to plug in between the two units. So maybe I should mention that the units on the left here is where we have all the lasers, all the electronics, all the control system, and the power supplies. We've also worked a lot on making the instrument easy to operate. It's not intended to be used by quantum physicists, but by geophysicists who don't know anything about quantum physics, about optics, lasers, and so on. So everything in there is pretty much automated. The software is very intuitive. The device can be operated remotely through an internet connection, so we can make sure it's running correctly from a long distance. We can help the end users with the data that they're getting. So this came at the cost of a lot of engineering, but we had to do all that without cutting on the performance. And the performance that this kind of device can achieve is measuring gravity with 9-digit precision. I don't know if people in the audience are familiar with the figures involved in gravity measurements, but basically the daily changes in gravity due to tides, so just because the moon is pulling on us, is roughly 10 to the minus 7. So it means that we can resolve that with a very high precision. Just another figure which I like is the vertical gradient when we are moving away from the Earth. 10 to the minus 9 corresponds to roughly 3 millimeters. So with this device, we can sense a change of gravity corresponding to a difference of elevation of 3 millimeters. And with that, basically, we can install it somewhere and have an information on what's going on below the surface. So if, for example, there is some water accumulating below the surface, the gravity on the surface will change and we can measure that. Another application is volcano monitoring. We took part in a European project called Newton G, and almost 5 years ago now, we installed an instrument in an observatory here near the top of Mount Etna volcano in Sicily. The conditions are quite hard. As you can see, in the winter, we get some snow, so it's not possible to access the instrument. There's a lot of acid gases coming out of the volcano and so on. So it's quite hard conditions to be doing precision measurements and quantum physics. But the instrument has actually proven that it could operate reliably in those conditions. And it's now beyond the proof of concept, and it's integrated into the volcanoes monitoring system. And if you're interested at what the geophysicists do with the data, you can look at these papers where basically gravity is used to get information on how much mass is accumulating below the crater and how much mass is being exhaled during the eruptions, and trying to understand what's going on. So it comes as a complement to GPS and monitoring gas outlets and so on. So despite being a quantum system based on a quite new technology, it's been working very reliably and in extremely robust manner over the past years. This was just an example. We've actually built and delivered, I think now it's something like 16 or 17 of these units. They're in operation pretty much everywhere around the world. Some of them in nice observatories, like here in Germany on the top right, but some of them have been on field missions. So this is a French campaign in the French Caribbean. This is Mount Etna. The bottom left plot picture, sorry, is measurements in Germany. We've had the device go to Antarctica for a field measurement. And so what I want to highlight here is that despite quantum technologies being a pretty young field of technology, we're managing to get a very reliable and mature instruments out of there. And of course, this is ongoing work. And I have just one slide to give you an idea of where we're heading now. This is very recent results we've obtained with a new type of instrument, which we call a differential quantum gravimeter, which basically can measure both gravity and its vertical gradient. So we drop two clouds of atoms at the same time. Basically, it's like having a 2-pixel camera. And by doing that, we can get very good resolution because we reject a lot of common mode effects between the two clouds. And some of my colleagues went to Lisbon in Portugal a few months ago. And I don't know if you know, but Lisbon is a city where there's a lot of archaeological remnants pretty much everywhere. And they conducted a survey here in the city center in what we can call challenging conditions. The day the picture was taken, the weather was nice, but they actually had some rain, quite a lot of wind, people passing by. There's a tramway line nearby. But despite that, they were able to map out the area enclosed by barriers here, and getting a map of both gravity and the gradients. And from there, we're working with a company in Italy called Geored, and they could perform an inversion of the data and infer what's below the surface. And it corresponds to what we are expecting, which is an old sewage system from the 18th century. And you can see that's without any assumption on the shape, they were able to render quite well both the size, the depth, and the shape of the conduct. So this is the kind of things that we can do with quantum sensors applied to geophysics. I hope that with this very short introduction, I was able to convince you and give you a taste that these sensors are now mature and operational. As I said, we've installed over 15 of these in pretty much all types of conditions we could expect. We are working on next generations. The idea is to go from static measurements to large-scale surveys. The differential quantum gravimeter I've just showed you, we're working in the frame of another project to put it on a rover to do some autonomous mapping. We want to put these devices on ships, boats, possibly drones also, which Exail happens to make for large-scale surveys. This can be both for navigation applications, but also for geophysics, like monitoring large-scale reservoirs or detecting geophysics features. We are also involved in space missions, next generation gravity mapping missions from space. Well, again, I think this highlights the maturity of the technology. And on the question of what people can do for us, well, we are open for collaborations with people from the geophysics and mining community. We're quite interested in new use cases, in evaluating how this kind of technology can help and can be coupled to other sensing approaches, and seeing how we can build possibly new projects and so on. And with that, I would like to thank you for your attention.